All right, so let's share the screen. All right, so this chapter is going to be on interference of waves. Interference of waves. What we call interference is when two waves meet at the same point at the same time, okay? So the effect will be the effect of both waves. So this is meeting of two waves, meeting of two waves or more, but we're going to use two waves uh, at the same point at the same time, at the same point at the same time. All right, for example, let's say you disturb water over here. Let's say you have water over here, you disturb this point, you can get waves like this, spherical waves like this, right? And then let's say you have another point over here. Suppose you disturb both of this at the same time like this, like this. So a molecule over here is going in instruction from this disturbance and this disturbance, okay? So the effect on this molecule over here is going to be the sum of both disturbances, right? So simply, the net wave is going to be the sum of two waves, okay? So let's say you have y1 is a1 cosine omega t minus kx1, if you're dealing with harmonic waves. And let's say y2 is a2 cosine of omega t minus kx1, okay? So the net effect of this molecule is going to be the effect of the sum of the effect of both waves. So you would say simply y net equals y1 plus y2, okay? So it's simply the algebraic sum of the two waves. You've got instructions coming from this disturbance over here. You got instruction coming from this disturbance. This molecule receives both instructions and moves accordingly. And so the interference, the net effect of the interference would be simply the sum of the two waves, okay? Now we're looking at a particular molecule over here. So that means Rx is a constant. So basically we have time oscillation. So this molecule over here is harmonic oscillation at a given point, okay? So we can simply write its motion as y cosine of omega t and then a phase angle beta 1. We're looking at a particular location over here. So this is a constant, okay? So this molecule over here will be moving like a harmonic oscillator, all right? So we don't have to deal with this variable x, it will just be a constant beta, okay? So we're gonna have two instructions. Y1 is a1 cosine of omega minus beta 2, and y2 would be a2 cosine of omega t minus beta 1, okay? Now we'll see later that the difference between these two phase angles plays an important role in the way the two waves are added, okay? The difference between two waves determines how the two waves are added together. So I want to look at these two phase angles before we start. I want to see as origins of the phase angle. So let's look at origins of or sources of the phase angle. Sources of the phase angle. So normally the wave would be given like this: y equals a cosine omega t minus kx. And then if you've got a non-zero value at t equals 0, x equals 0, you'll have another phase angle over here like this, okay? This would be the general expression of the wave. Now, the phase angle between two waves, let's say this one is t1, x1 over here, and then you have another one, y2, a2 cosine of omega t2 minus kx2 minus phi, okay? There are three sources for the difference between these two angles. You can have a source because of the difference between these two angles. These are angles at x equals 0 and y equals 0, phase angle. You can also have a contribution to it because of the distance traveled by the two waves. If the distance traveled by the two waves, by the time they meet at the same point, is not the same, then you'll have a difference caused by this difference. We call that path difference. And the two waves travel different times. By the time they meet, you'll also have a contribution of the phase difference because of the time traveled by the two waves. Let's say the two waves meet over here. Let's say this wave comes over here like this. Let's say this wave comes over here like this, okay? Let's say this travels x1, this travels x2. If these two distances are different, you'll have a contribution to phase angle because of the change in distance traveled, okay? We call that path difference. Also, if they travel different times to get here, we'll have a contribution to the phase difference because of the time traveled by the two waves, okay? So we want to get an expression for the phase difference between the two waves in terms of this difference, the path difference, and the time difference, which is called time lag. Okay, so I'm going to write like this. I'm going to say let x2 be x1 plus delta x, where delta x is the path difference, the change in the distance traveled. Now I don't need the subscript. I can just write x plus delta x. And then I'm going to say let t2 equals t1 plus delta t, where delta is the time lag or the time difference of the time traveled by the two waves by the time they get there. Okay, so I can just say t plus delta t over here. Okay, so let's write the two waves in terms of this. So the first one, y1, would be a1 cosine of omega. This would be just t, for example, the first one, minus k times x minus phi 1. Okay, this would be the first wave. The second wave, according to substitutions over here, is going to be like this, a2 cosine of, now this becomes t plus delta t, okay? And this becomes minus k x plus delta t, and then you've got minus phi 2 over here, okay? So let's look at the phase angles of these two waves. The phase angle for this one is kx minus phi 1, okay? Let's call that beta 1. My beta 1 is kx minus beta 1, okay? This is the general formula of the wave minus beta, okay? So the beta for this one, or beta 1, is kx plus phi 1, okay? The phase angle of the first wave would be beta 1 equals kx plus phi 1. How about this one? This one, we have minus omega delta t. If I put a minus over here, it's minus delta t. So from this one, I'm going to have negative omega delta t. And then I have, well, I mean, let's write first at the positive. Okay, so what I have is, I've got omega delta t over here. Okay, let's put omega delta t. This omega times delta t, we have this factor over here. And then you've got minus kx, all right? And then you've got minus k times delta x over here. This is x over here, minus k delta x over here, minus k delta x. And then of course we have minus phi 2. I'm talking about beta 2 over here. And then we've got minus phi 2 over here. All right. So these are the phase angles of the two waves. All right. So, well, this is the actual, this is a negative beta 2. Okay, so let me put beta 2 like this. Beta 2 would be kx and then plus k delta x, and then it would be minus omega delta t, and then minus phi 2. Okay, so the path difference or the phase difference, beta 2 minus beta 1, you see, the kx goes away. Do you see that? And then you've got k delta x, you've got minus omega delta t, and then you've got plus phi 2 minus phi 1. This is the difference between the two waves, okay? So the source for the phase change is 3 parts. This is the source for the phase difference due to the path difference or difference in distance traveled. This is omega times the change in time traveled by the two waves, and then these are the phase angles at t equals 0 and x equals 0, okay? So this is the source of phase change for the two waves, all right? Okay, now we're gonna look how the two waves are added. So we're gonna have the following two waves. So you've got, let's say y1 is a1 cosine of omega t minus beta 1, and then y2 is a2 cosine of omega t minus beta 2. Okay, so we want to add these two waves. So y net, the net wave, is the sum of these two. A1 cosine of omega t minus beta 1 plus A2 cosine of omega t minus beta 2. Now, these are harmonic oscillators, both of them. The sum of two harmonic oscillators is also a harmonic oscillator, okay? So we want to express the sum of these two as a harmonic oscillator, something like this, A cosine of omega t minus delta. The sum of the harmonic oscillators is also a harmonic oscillator. Now our goal is to express A in terms of this variables over here and express this phase angle in terms of this variables over here, okay? So what we're going to do is we're going to expand these two functions, this over here. I'm going to use the following formula. Do you know this formula? Cosine A minus B. We're going to use the expansion formula, okay? This is cosine of A, cosine of B, plus sine of A, sine of B, right? Do you know that formula? It's the cosine of the difference between two angles, all right? So I'm going to do that to both of them. So what I have is y1 equals a1 cosine of omega t minus beta 1. Okay, when I use this formula, it becomes a1 cosine omega t cosine of beta 2 plus a1 sine omega t sine beta 2. Okay, that is the expansion of this one over here. And then I'm going to expand the same thing for, I'm going to do the same thing for the second one. The second one is a2 cosine of omega t minus beta 2, right? So we get a2 cosine of omega t cosine of beta 2, and then plus a2 sine of omega t sine beta 2, all right? Now the net wave is the sum of these two, right? Y net equals y1 plus y2. Okay, so we're going to put them together. All right, so we have this one over here. Let me start over here. This one is, let me start over here so that I have space. A1 cosine of omega t cosine of beta 2 plus A1 sine omega t sine beta 2. Again, the second one is A2 cosine omega t cosine beta 2, and then we have A2 sine omega t. Well, this is 1, this is beta 1. Okay, this is beta 1 over here. And then you've got beta 2 and then sine of beta 2. Okay, the sum of these two waves. So now what I'm going to do is I'm going to factor out cosine omega t. Okay, you see, these two have cosine omega t, this two have sine omega t. So when I do that, I find this one. This equals cosine of omega t. Okay, I'm adding this to now. So you've got a1 cosine of beta 1 plus a2 cosine of beta 2. Okay, plus these two terms have sine. So I'm going to factor out sine. Okay, so you've got sine omega t, and then you've got a1 sine of beta 1 plus a2 sine of beta 2. Okay, so this is the sum with cosine and sine factored out. Now I'm going to change my constants to a and delta. Okay, you remember we're trying to express it like this. The sum of two harmonic oscillators is also harmonic oscillator. I'm trying to write it like this. Okay, so I'm going to say, I'm going to replace this constant in terms of a and delta. Okay, so I'm going to say let this constant over here, a1 cosine beta 1 plus a cosine beta 2, let a1 cosine of beta 1 plus a2 cosine of beta 2 be a times cosine of delta. Okay, and then I'm going to say let the second one, a1, the sine of beta 1 plus A2, the sine of beta 2 equals A sine gamma, okay? So all I'm doing is using different constants than this ones, okay, for this one, okay? So this one is A times cosine of delta, and this is A times sine of delta. So I've got the following now, okay? So my Y net is now the following. You've got A cosine of delta times cosine of omega t, okay? And second one is A, the sine of delta times the sine of omega t, okay? You see that? Now we combine these two using the same formula. You remember this formula over here? This formula? Now we're going backwards. Cosine A cosine B plus sine A sine B equals cosine of A minus B, okay? Using that formula, I get the following. Y net equals A cosine of omega t minus sigma, okay? So you see, the sum of the two harmonic oscillators is also a harmonic oscillator, all right? Now what we have to do is we have to relate A with this values over here, and the phase angle also with this values over here, okay? So we're going to go back over here to relate them, okay? So I've got, I'm going to square both sides over here, all right? So I've got A squared cosine squared gamma, and then we call the square of this one, A1, well, let me just put cosine of beta 1 plus A2 cosine of beta 2 squared, okay? And then the other one, you square it, you get A sine square of gamma is this one. We're going to square this one, okay? So you've got A1 sine of beta 1 plus A2 sine of beta 2 squared, okay? Can you tell me what's the square of this? What's the sum of these two? A cosine square of delta and A square sine square of delta. What's the sum of these two? Just do A cosine squared. You can factor out A squared, and then you'll have cosine squared plus sine squared. What is cosine squared plus sine squared? 1.
1.
Right? Okay. So this, if I add this together, this side is just A squared. Okay? So let's do just this one. Now, this would be just perfect square. Okay? So you've got A1 squared cosine squared beta 1, and then you've got twice A1, A2 cosine of beta 1, cosine of beta 2, and then of course the square of the second term. I'm using the formula for perfect square, okay? You've got cosine squared beta 2. And then the other one, the same thing. You've got A1 squared sine squared beta 1, the square of this, plus twice the product of this. That is 2 A1, A2 sine beta 1, sine beta 2, and then you square this one, okay? You get plus A2 squared sine squared beta 2, okay? All right. Now, can you tell me what the sum of these two is? Just these two terms. You can factor out A1 squared. So you have cosine squared beta and sine squared beta, right? So the sum of these two is just A1 squared. All right. How about these two terms? These two terms, you see, A2 squared cosine squared beta 2, A2 squared sine squared beta 2. You factor out A2 squared, you've got cosine squared plus sine squared. This also will give you A2 squared. You see that? So this one is, these two give you A1 squared. This one, these two will give you A1 squared. And then we can factor out to A1, A2 from these two terms over here. So you get the following. We have A squared, okay? The sum of these two, we get A1 squared. A1 squared. The sum of this one and this one, we get A2 squared because they're sine squared and cosine squared, okay? So you've got plus A2 squared. And then look at these two terms, this one and this one. They have this common, 2A1, A2 to A1, A2, and then cosine beta 1, cosine beta 2, plus sine beta 1, sine beta 2, right? And then I can write this as, maybe let's over here, you've got 2A1, A2. I factor this out. I get cosine beta 1, cosine beta 2, plus sine beta 1 sine beta 2. Okay. Now, can anybody tell me what this equal to using the cosine formula? Remember this formula over here? I wrote over here. This formula over here, cosine A cosine B plus sine A sine B equals cosine A minus B, right? So this one over here is simply cosine of beta 2 minus beta 1. This is cosine of beta 2 minus beta 1. Okay? So I get the following. A squared equals A1 squared plus 8 squared plus 2 A1 A2 cosine of beta 2 minus beta 1. You see? So I got a formula for the amplitude of the net wave in terms of the two amplitudes and the two phase shifters. We take the square root, of course. We get the following. So this is the formula for the amplitude of the net wave. We have A1 squared plus A2 squared plus 2 A1 A2 cosine of beta 2 minus beta 1. So yeah, you remember I told you this phase shift plays an important role how they're added. That's why, you see, the amplitude depends on the phase difference between the two waves. All right. So this gives you the formula for the amplitude of the net wave in terms of the amplitudes and phase angles of the two waves. All right. But we still have to find the phase angle of the net wave. That's delta. We have to find this one. All right. Again, we're going to use this two formulas. You see, this is A sine delta. This is A cosine of delta. If I divide this by this, I'll get tangent. Do you see that? This divided by this is tangent. Maybe I'm right again. I'm right again over here. So I've got the following. A, the sine of delta, according to our assumption, is A1 sine beta 1 plus A2 sine beta 2. Okay? And then A cosine of delta. Delta is the phase angle of the net wave. I have A1 cosine of beta 1 plus A2 cosine of beta 2. Okay? Now I'm going to divide this by this. This equation by this equation. What is sine divided by cosine?
Tangent.
Peter, Mike, what is it?
Tangent.
Tangent. Very good. So I'm going to divide this. So I get tangent of delta over here. Tangent of delta. And that is A1 sine beta 1 plus A2 sine beta 2 divided by A1 cosine of beta 1 plus A2 cosine of beta 2. Okay? So how do I get a formula for this angle, for delta? Tan inverse, right? So we have a formula now. This delta equals the tan inverse of A1 sine beta 1 plus A2 sine beta 2 divided by A1 cosine of beta 1 plus A2 cosine of beta 2. You see that? We have a formula for the phase shift too. Okay? All right. So these are the formulas for the phase angle of the net wave and the amplitude of the net wave. So let me just recap what I've done. So what we're saying is if y1 equals a1 cosine omega t minus beta 1 and y2 equals a2 cosine of omega t minus beta 2, then we're saying y1 plus y2 equals a cosine of omega t minus delta over here, provided a is given by this formula over here and delta is given by this formula. Okay, so you see the two harmonic oscillators, the sum of two harmonic oscillators is still harmonic oscillator. The only difference is in the amplitude and the phase angle. So this is the amplitude of the net wave, and this is the phase angle of the net wave. All right. Now let me go to my desktop and show you one graph. Where is it? This need amplitude. All right, let me run this. You can see it, right? You see the graph? All right. So I'm adding two waves with a phase shift. You see, this is one of my harmonic waves. I'm using a 0 phase angle, and then there's a phase difference over here. Okay, you see that fine? That's a phase difference. So look, these two are, let me show you now. You see, the phase shift is the shift in the two peaks. These are the two waves I'm adding. The blue and the orange are the two waves I'm adding, okay? And then the third wave over here is the sum. The green is the sum of these two, okay? So I've got these two harmonic waves, the blue and the orange, and they have the same frequency. The only difference is they have phase shift over here, okay? So over here, I'm just changing the phase shift in terms of pi. So let's see what happens. Let's start from 0. So you see this is the amplitude when the two waves match. The two waves match when their phase shift is 0 or 2 pi or 4 pi and so on. So let's move it now. Let's increase the phase shift. The phase shift in terms of pi, okay? So you see, this is a phase shift. The separation between the two peaks is what the phase shift is. So as the phase shift increases, you see the amplitude decreases, okay? Now eventually, when the phase shift is pi, which means they are out of phase, they're oscillating, you see? Now they're moving in opposite directions. You see when this goes up, this goes down. Basically, they cancel each other. We're adding them, okay? So you get a 0 amplitude over here. You see that? If I keep going, you see, it keeps increasing. And when the two waves match, that is when their phase shift is 0 or 2 pi, again, I get a maximum, okay? Do you see that? And so on. So when the phase difference is pi, they cancel each other, you get the minimum. And then when the two waves are in phase, when they match each other, you get the maximum, okay? So you see that's how the sum depends on the amplitude. You see A over here, it depends on the phase shift over here. And you can see from this graph. When they match, when the phase difference is 0, you get the maximum. When they go in opposite directions, when the phase shift is pi, you get the minimum, 0 and so on, okay? All right, so let me go to my paper, okay. So this one, all right. Okay, now probably the most common case we'll deal is the case where the amplitudes are equal, okay? So let's simplify these two formulas for the case where the two amplitudes are equal, okay? Now let's see if, well, let me put this in bracket like this. So if A1 equals A2, we have the following simplification, okay? So the general formula is A equals square root of A1 squared plus 8 squared plus 2 A1 A2 cosine of the phase difference, beta 2 minus beta 1, right? Now let's just put A1 for A2, okay? So we have square root of A1 squared plus A1 squared plus 2A1 times A1, 2A1 squared, okay? And we've got cosine of the phase difference between the two waves, all right? So you see you got 2A1 squared, 2A1 squared, we can factor out 2A1 squared, all right? So the amplitude equals, we have root 2 coming out and A1 coming out, and then square root of 1 plus cosine of beta 2 minus beta 1, okay? Do you see that? Now, do you know the following double angle formula, cosine squared of x equals cosine of 2x plus 1 over 2. Do you know this formula? Double angle formula? Okay. Or if I decide to put y over here, it becomes cosine squared of y. This becomes y over 2. And then I can put cosine of y plus 1 over 2. Okay? So that tells you this one over here. This one is, let me put over here, 2 times over here, right? So this one equals 2 times, so cosine square of beta 2 minus beta 1 equals 2 times cosine square of beta 2 minus beta 1 over 2. You see that? Beta 1 over 2. I have this formula using this double angle formula over here, okay? So the amplitude is, we've got root 2 a1, and then we've got square root of this one, 2 cosine square of beta 2 minus beta 1 over 2, right? So I can take the square root out. So that gives me 2 times a1, and then the square root is going to be absolute value of cosine of beta 2 minus beta 1 over 2. Okay, so this is if the two amplitudes are equal. Okay, so we have this formula if the amplitudes are equal. If the amplitudes are equal. This is the most common case we're going to deal with. Okay, so if the amplitudes of the two waves are equal, you can just use this formula, 2a1 times the cosine of half of the phase difference. Okay, now we're going to look at 2 special cases. Remember in the graph we saw that when the 2 waves merge, you get maximum sum. When the 2 waves go in opposite directions, we get the minimum. Okay, these are the 2 extremes. They're called constructive interference and destructive interference. Okay, so let's define constructive interference. Constructive interference. This is interference with the maximum possible effect. This is interference with the maximum possible effect. The maximum possible effect. Okay, so let's get an expression for the maximum. This is our formula. A equals square root of a1 squared plus 8 squared plus 2 2a1 a2 cosine of the phase difference. Okay, so what do you think is this maximum? What's the maximum value of cosine? How much? 1.
1.
So a max, the maximum value, I just put 1 for cosine, implies cosine of beta 2 minus beta 1 equals 1. Okay, so the maximum value in this case is the square root of a1 squared plus 8 squared plus 2a1 a2. Okay, what is the factorization of this? Can you tell me? It's a perfect square. What's the factorization of this? a1 squared plus 8 squared plus 2a1 a2.
A1 plus A2 all squared.
Very good. So this is square root of a1 plus a2 squared. Okay, now we're going to assume the amplitudes are positive. They can be negative, but you can easily change it to a positive. To change a negative amplitude to a positive amplitude, all you have to do is add a pi to the phase angle. Okay, so let's say you've got -5 cosine of omega t, let's say plus pi over 2. If I want to change it positive, all I have to do is 5 cosine of omega t plus pi over 2. If I add pi, that absorbs the negative. Okay, so you can easily change a negative amplitude to a positive by adding pi to the argument. That's what pi does. It changes the negative. All right, so we're going to see if the amplitudes are positive. So that tells me the maximum amplitude is simply the sum of the two amplitudes, okay? So this is the maximum value. So for constructive interference, the net amplitude is the sum of the two amplitudes, okay? And what's the condition for this? The condition for this is that the cosine of the phase shift equals 1, okay? So let's look at the condition of constructive interference. Condition for constructive interference. Okay, we have already stated our condition. Our condition is that the cosine of the phase difference with beta 2 and beta 1 equals 1. This is our condition. When is cosine 1? Cosine in 1 at 0, right? Over here is 0. Over here is negative 1. Okay, over here is 0. So cosine is 0 only at 0 and 2 pi and 4 pi and so on. An integral multiple of 2 pi, okay? So cosine equals 1 when the angle is an integral multiple of 2 pi or an integral multiple of 360 degrees. So we can say that this implies beta 2 minus beta 1 equals 2n pi, where n is integer, okay? So this is the condition. The condition is that if the phase difference between the two waves is an integral multiple of 2 pi, then we'll have a constructive interference, okay? Well, that actually means beta 2 minus beta 1 equals, let's say, negative 4 pi, negative 2 pi, 0, 2 pi, 4 pi, and so on. It's an integral multiple of 2 pi. Basically, this means when the two waves match. We have already seen it. You see, when the phase shift is either 0 or 2 pi, the peaks of the two waves match. That's when you get the maximum, okay? So this is a condition of constructive interference. So when the phase shift, this is, can you see my hands? This is what constructive interference is.
No.
The two waves move up and down together, okay? That means the phase shift is either 0, if you add 2 pi, nothing changes. So 0 plus 2 pi, 4 pi, 6 pi, and so on, you get constructive interference, okay? So to find out whether two waves interfere constructively, all it is, you find the difference between two waves. If that angle is one of this, then they interfere constructively, okay? The other extreme is destructive interference. Destructive interference. Again, this is the other extreme. It is interference with a minimum possible effect. This is interference with the minimum possible effect. The minimum possible effect, okay? So we have to find the minimum, all right? Our formula is the following: A equals square root of A1 squared plus A2 squared plus 2A1 A2 cosine of beta 2 minus beta, okay? So to get the minimum, we have to replace this by its minimum value. What's the minimum value for cosine?
-1.
-1, very good. So that we're going to do. So A minimum would be simply A1 squared plus 8 squared. We get negative from here. We have -2 A1 A2, okay? What's the factorization of this?
A1 minus A2.
A1 minus A2, right? So this is A1 minus A2 squared, and then we take the absolute value. So for the minimum amplitude you can have is the absolute value of the difference between the two amplitudes, okay? So this is your amplitude if the two waves interfere destructively, okay? So for destructive interference, the amplitude of the net wave is the difference between the amplitudes, okay? Now, if you look at the graph we just saw, the two, we get the minimum when they go in opposite directions. Do you see that? When they go like this, in opposite directions, we get the minimum value. So that tells you the condition is that the phase shift should be pi 3 pi and so on. But let's look at it. Condition of destructive interference. We have already stated the condition, destructive interference. Okay, the condition is that this should be negative. That's what we did, okay? The condition is cosine of beta 2 minus beta 1 equals -1, okay? So when is cosine negative? Cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, right? And then over here will be 0, so it's only here. So pi, you keep adding to pi, 3 pi, 5 pi, 7 pi, and so on, will give you -1, okay? So the condition is an odd integral multiple of pi, okay? So this implies this phase difference over here should be like -7 pi, -5 pi, -3 pi, -pi, I put too much, pi, 3 pi, and so on, 5 pi, and so on, okay? How do you write that in terms of integer? This is an odd integral multiple of pi. So I can say 2n minus 1 times pi, okay? So the condition for this is beta 2 minus beta 1 is an odd integral multiple of pi, okay? If you put 1, you get pi. If you put 2, you get 3 pi. If you get 3, 5 pi, and so on. So two waves interfere destructively if the phase shift in the two waves is an integral multiple of pi, okay? So let me show you graphically. So these two waves, do you think this will interfere destructively or constructively? If I add these two waves, do you think they interfere constructively or destructively?
Constructively, because they have the same phase.
Yeah, they're going together. They're going to add up each other, okay? And this is the phase shift is 0. You see, this is too much. So the phase shift is 0. You're going to have constructive interference. You have the maximum possible effect. In other words, it's going to be the sum of these two waves. It'll go like this, the sum of two waves. How about if you have like this? Let's say one of these waves goes this way, but the other one goes like this. Okay? So do you think this will interfere constructively or destructively? They're going opposite directions. When this goes up, this goes down. So they cancel each other. Okay? How about the phase shift? You see, from here to here is one cycle. This is 2 pi. But this is the phase shift of two waves, which is pi. Okay? So two waves interfere destructively when the phase shift in them is pi, or you keep adding 2 pi. Adding 2 pi doesn't change anything. Okay? So the two waves will interfere destructively if this phase shift is pi, or you keep adding 2 pi, 3 pi, 5 pi, and so on, or an integral multiple of pi. Let me put n is integer. Okay? So these are the two special cases. Two waves interfere constructively if the phase shift is an even integral multiple of pi, and they interfere destructively if the phase shift is an odd integral multiple of pi. Okay? Do you have any questions so far? Okay. Now we're going to look at an example of interference. That is the experiment we did last time, standing waves. Okay? So we're going to look at standing waves. Standing waves. These are, as you've seen before, these are waves with equally spaced points of zero vibration. This is waves with equally spaced points of zero vibration. Points of zero vibration. Okay, you have already seen it. You've got this kind of wave over here. Let's say this goes like this, and then this goes like this. If you've got this kind of wave where you've got points of zero vibration, these molecules vibrate vigorously, but then there are molecules that do not vibrate in between, okay? So such kind of a wave is called a standing wave, all right? With a wave with points of zero vibration separated by equal distances. Now, these points of zero vibration are called nodes. These points of maximum vibration are called antinodes, okay? These are the maximum points are called antinodes. The minimum points are called nodes. Now, what do you call this interval over here? Remember, this is a loop. This is a loop. Okay, so these are the terminology you're going to use. So nodes refers to this point, antinodes refers to the maximum points, and the separation between 2 points of zero vibration is called a loop. Okay, now our goal is to look at the physics of this kind of motion. So why do standing waves happen? Standing waves happen because of the interference of 2 waves, okay? For example, let's say you have this string over here. Let's say it's clamped over here. And let's say you excite a wave over here. That wave is going to travel like this. But if it's clamped over here, it has nowhere to go. It reflects, okay? Now, if this obstacle is denser or, I mean, greater than this medium over here, there's a phase shift of pi. It goes in opposite direction like this. So you've got to, remember, this is still oscillating back and forth continuously. So you've got a wave coming from here, and then you've got a wave reflected from here. It's the sum of these 2 waves that gives this kind of characteristics. If you look at the molecule over here, it has to respond to 2 waves. To the wave coming from here, and then to the wave go all the way over here and back over here. It's the sum of the incident wave and reflected wave, okay? So standing wave happens or occurs, standing wave occurs when an incident wave interferes with a reflected wave, This is the cause of a standing wave, okay? It's the sum of an incident wave and a reflected wave. Now let's take a string of length L, okay? Let's say this distance over here is L, okay? Let's say this distance over here is X. Let's say the 2 waves meet over here. So you've got a wave coming directly over here. So this wave will travel a distance of X by the time it reaches this point over here. But the reflected wave is going to go like this. It will go over here, which is L, and then comes back over here, which is L minus X, okay? So you've got this distance over here is L, and this distance over here is L minus X, okay? So the distance traveled by the reflected wave is L plus L minus X, but the distance traveled by the incident wave by the time they meet over here is just X, okay? So let me represent the incident and reflected by YR and YI, okay? So I have is YI equals, and I'm going to assume 100% reflection so that the amplitudes of the reflected wave and incident wave will be equal, okay? Anyway, they have nowhere to go over here. It's going to be reflected 100%. Okay, normally what happens is some of it gets transmitted, some of it gets reflected. But you see, if you've got a hard clip over here, there's nowhere to go. So it can come back 100%, okay? So that means the reflected wave and the incident wave are going to be equal. Okay, so for the amplitude, just equal. Let me say, assuming 100% reflection, assuming 100% reflection, we're going to put the 2 amplitudes equal, AR equals A, okay? So the incident wave would be A cosine of omega t minus K X is the distance traveled by the incident wave, okay? And then the reflected wave would be A cosine of omega t minus K times X reflected. But remember, there's a phase shift of pi on reflection. Okay, so we're going to add pi over here because when it reflects from a denser medium, it returns in the opposite direction. So because of that, there's another phase shift over here. Okay, so what we have is xi is simply the distance x. This is distance traveled by the incident wave. Okay, so I've got distance traveled by the incident wave is simply x. The distance traveled by the reflected wave is this distance over here, L, plus this distance from here to here, which is L minus x. Okay, so we've got L minus x. So this is 2L minus x. Okay, so these are the distance traveled by the incident, the reflected wave by the time they get to this point and they add up together. All right, so let's put that over here. So the incident wave is a cosine of omega t minus kx. Okay, the reflected wave is a cosine of omega t minus k. You see, the distance traveled is 2L minus x. Okay, 2L minus x. And then we have also minus pi over here. Okay, so there are two waves. All right. Now remember, when we add waves, we need the phase differences. Okay, so let's add the beta. This is my phase angle for the first one. So the phase angle of the incident wave is simply kx. Remember, we're looking at a particular point. So this x is a constant. All right. So we're talking about a phase angle over here. So this is my phase angle for the incident wave. All right. So the phase angle of the incident wave is k times x. The phase angle of the reflected wave is this one, k times 2L minus x, and then we got plus pi. Okay. So this is the phase angle for the incident wave. This is the phase angle for the reflected wave. All right. So what's the difference? The difference, beta reflected minus beta incidence, is k 2L minus x plus pi minus beta 1 minus kx. Okay, so what do you get? We get 2KL minus kx plus pi minus kx. Okay, so you've got 2KL minus 2kx plus pi. Okay, now we can factor out 2k. This is 2k. You've got L minus x plus pi. Okay, so that is our phase difference. 2k times L minus x plus pi. Let's just remind you the variables. L is the length of the string from here to here, and x is the point where they're meeting. This is x, the point where they're meeting. All right. Now we get an expression for the amplitude because we have a formula, right? Our formula is the amplitude of the net wave. They're being added together is this one. We're saying the two amplitudes are equal, so you've got a1, a squared plus a squared plus 2a1 times a2, which is a squared, okay? And then cosine of the phase shift, which is 2k L minus x plus pi, okay? So what happens if we add pi to a function? What is cosine of x plus pi? Can you tell me? If you add a pi, you're rotating by 180 degrees. So you just make it negative. Okay? This one is negative cosine of x. If you want, you can expand it using the cosine formula. But if you add a pi, basically rotating by 180 degrees, it just becomes a negative. But if you want, you can do like this: cosine of x, cosine of pi, minus sine x, sine of pi. Okay? Which one is 0? Cosine of pi is -1, right? And this one is 0, so you get negative cosine of x, okay? But if you add pi, you just turn to negative. So I'll take off the pi and put a negative over here, okay? Oh, I should put one over here. I made both of them the same. Let me just put, well, let me just say a net over here. I don't know, because I already said it's a. So let's say this is n net and this is a, okay? So I have the following formula for the amplitude of the net wave. I've got net wave equals, you see I've got 2a squared, and then minus 2a squared, and then you've got cosine of this one, which is 2k L minus x, okay? This is 2k L minus x. The pi turn this positive into negative, right? So let me factor out the 2, or well, 2a squared, okay? So I've got root 2 times a, and then I've got square root of 1 minus cosine of 2k L minus x, okay? That's what I have so far, all right? Now we're going to use the double angle formula for a cosine. Do you remember that? Do you remember this formula? Sine squared of x equals 1 minus cosine of 2x divided by 2. Do you remember that formula? Or this equals 2 times this. Or if I decide to call this y, this becomes y over 2. So you've got 2 sine squared of y over 2 equals 1 minus cosine of y. Okay? So we're going to replace this over here by this one. All right? So we have the net is square root of, but root 2, we already have root 2a over here, root 2a. And then I'm going to replace this by this one. So I get 2 times sine squared, but remember I got divided by 2. You've got 2k L minus x over 2. Okay? So we have the following. A net equals, you see, I've got another root 2 over here. So it's going to be 2. So you've got 2 times a, and then this is absolute value of sine. Absolute value of sine of, remember this 2 goes away, k L minus x. Okay? So this is the amplitude of the net wave. All right? So the amplitude of a net wave is a sine. What does that tell you? Sine can be 0 at certain locations, right? So that's where the points of 0 vibration come from. You remember the general, this is the general solution. You've got A net times cosine of omega t minus, this is the general solution, right? For the sum of these two waves. Do you see that? This is the general solution for the sum of the two waves. All right. So what this tells us is this over here is a sine function. Okay? This amplitude over here is a sine function, which means can be zeros at certain locations. Okay? So you've got the rapid changing time function over here. So let's look at the solution. So you have a rapidly changing time function over here like this. And then you're multiplying it by the net amplitude, which varies like a sine as a function of x, okay? So you multiply this by function something like this. Something like this. So what do you get? You see over here, 0. Over here, 0, because you're multiplying by 0, okay? So what's going to happen is, in this case, you will have a weight like this, then you have 0 over here, another wave over here, 0 over here, and another wave over here, and 0 over here. That's how you get the loops, okay? You've got a rapidly changing time function, and then you multiply it by a sine wave like this. These points over here are going to be 0. So you see, you get loops between the points of 0 vibration over here. So this standing wave occurs because the product of a rapidly changing time function multiplied by the amplitude, which varies like a sine as a function of x, okay? So this is the cause of a standing wave, because the sum of the two waves results in the product of a rapidly changing time function and the amplitude that varies as a function of x, okay? So when you have a rapidly changing time function, and then you multiply by a sine function, where 0 certain locations over here, when you multiply them, you get a standing wave, okay? So that is the cause of a standing wave. All right. Now let's see what we have at x equals L, at the point of reflection. At point of reflection, at point of reflection was the value of L of x. You see the point of reflection is over here. Where did I draw the line? Over here. This is point of reflection, and that's L. At the point of reflection, x equals L, right? So let's see what's the value of the amplitude as a point of reflection. Well, it's clamped, we expect it to be 0, right? So at point of reflection, x equals L. And the amplitude is this one over here, 2a times sine. This is 2a times sine of k L minus x, okay? So a net at x equals L, what do you get? You see, what is sine of 0? If you put L over here, you get 0, right? So what's sine of 0?
0.
0. So what does that tell you? Is the point of reflection a node or antinode? No vibration at the point of reflection, so the point of reflection is a node. Okay, no vibration over there. So this implies point of reflection is a node. Point of reflection is a node. Okay, so there is no vibration at the point of reflection. The point of reflection is a node. Okay, now let's find the locations of the nodes. Locations of the nodes. Locations of the nodes. So what's the amplitude of the nodes? Remember, the nodes are points of 0 vibration, right? So at nodes, the amplitude should be 0, right? This net wave should be 0 at nodes, right? So what we have is a net is 2a, well, we have absolute value over here, sine of k L minus x equals 0 at nodes, right? So when is sine 0? Sine is 0 at 0.
Even multiples of
Over
pi.
2.
At pi over 2, it's 1, right?
Oh,
At pi
at
again
0
is 0.
and pi.
Huh?
At
Yeah,
0
it's
and
an
pi.
integral multiple of pi. Okay, so that tells you k, let's put m over here, L minus x, let's say the m1 over here, over here. This equals an integral multiple of pi, okay? So the sign is 0 when this expression over here is an integral multiple of pi. Let me put integer over here, right? Now remember, k is 2 pi over lambda. Do you remember that, wave number? 2 pi over lambda, right? So we have 2 pi over lambda L minus xm equals m pi, okay? So let's multiply this by lambda over 2 pi, okay? So what do you get? Pi goes away, you get m lambda over 2, okay? So this, remember, these are the locations of the nodes. That's why you put 0 over here, okay? So L minus xm is m times the wavelength divided by 2, okay? Or you get the location of the nodes, which is xm, is L minus m lambda over 2. Okay, so this gives you the location of the nodes. You see, when m is 0, you get L, which is the reflection point. We have already concluded that the reflection point is a node, okay? All right, now our goal is to find the size of one loop, okay? These are the nodes. The size of one loop is the distance between two nodes, okay? You've got, this is a loop, these are the loops. One loop is the separation between two nodes, okay? So let's look at the size of one loop. We used this idea in the lab last time, but let's derive it. Size of one loop. You can say simply take the two nodes, xm plus 1 minus xm, okay? You take two consecutive nodes, you find the separation, that'll give you the size of one loop, okay? So we can say this is L minus m plus 1 over lambda over 2 minus, and then the next one will be L minus m lambda over 2, okay? L cancels out, so what do you have? Simply m plus 1 minus m times lambda over 2. What's this one equal to? Just 1, okay? You see that? So the sine of one loop is half of the wavelengths. That's the idea we use it to we used in the lab last time, okay? So this is a very important conclusion. The size of one loop is half of the wavelengths. The size of one loop is half of the wavelengths, half of the wavelengths, okay? The size of one loop is half of the wavelengths. All right. Now we're going to introduce boundary conditions. We can restrict the waves, okay? So far what we've done is, what we have is, we have the string over here. This one is a node, but over here, we don't have any restriction. It can be like this or anywhere in between, okay? We didn't put any restriction over here, okay? So I'm going to restrict this one to be 0. I'm going to introduce boundary conditions. Boundary conditions. So the first case we're going to look is case 1 is let x equals 0 be a node, okay? Let, that is the point where the wave is initiated. Let x equals 0 be a node, okay? So we already know this is a node. Now we're requiring this to be a node. So the wave can be something like this. You can have like this. You can have 2 loops, 3 loops, 5 loops, and so on. You see, in the experiment we did, the vibrator was fixed at the end. So it's like this case. Oh my God. I'm sorry, I'm using my phone to take the video. All right. Okay. So let x equals 0 be a node. So what that means? That means at x equals 0, a net equals 0. Okay. At x equals 0, a net equals 0. Should I? Okay. Let me answer this. I think it's my wife calling. I'm really sorry. All right.
No worries, sir.
Yeah.
No worries.
But I thought I put a no disturb. I don't know what's ringing. All right.
We need a 5-second break anyways, probably.
All right. Okay. So now we'll introduce a boundary condition. We're going to require this to be 0. Okay. That means we're restricting the wavelengths that can occur in this wave. Okay. If you use any wavelength, you see it could be may not be 0 over here, but if you restrict it to be 0 over here, it's not going to be every wavelength. We're going to restrict the number of wavelengths. Okay. So let's work out this condition. We're going to set A net equal to 0 at x equals 0. This is A net. A net is 2a, the sine of k L minus x, right? So if you put 0, now we have A net at x equals 0, which is 2a, the sine of KL equals 0, okay? We're requiring the wave to be 0 over here. So this occurs when this is an integral multiple of pi, right? So this implies k times L is an integral multiple of pi, right? But remember, k is 2 pi over the wavelength, okay? 2 pi over lambda, let me put n over here, okay? So I've got 2 pi over lambda n equals n pi, okay? So what is my L? Oh, there's L over here. There's L over here, okay. So pi cancels out. Do you see that? We get the following condition. Lambda n equals 2L divided by n, okay? So it's only this wavelength where n is integer that can give you a standing wave that looks like this. You see? If you want to get standing wave that looks like this, it's only this wavelength. For example, for the first loop over here, the wavelength is going to be 2L. You put 1 over here, you get 2L. For the second one, you see, this one over here, the wavelength is going to be put 2, it's going to be L. For the third one, you've got something like this over here. You put 3 over here, the wavelength will be twice the length divided by n, okay? Now, this number n is related with the number of loops. So let's calculate the number of loops. Anyway, this is the n is harmonics. This is the number of harmonics, okay? You can say first harmonic, second harmonic, and so on. So let's see how the number of loops is related with the harmonics, okay? So for the number of loops, you got L over here, right? You divide by the size of one loop, which is lambda over 2. That'll give you number of loops, right? So number of loops, so let this n be number of loops, okay? And we know that one loop is lambda over 2. One loop is lambda, let's say lambda n over 2, all right? So the number of loops is the length divided by the size of one loop, which is this one, which is lambda n over 2, right? Lambda n over 2, or that would be 2L divided by lambda n, okay? But lambda n, this one over here. So the number of loops is 2L divided by lambda n, which is this one. You see lambda n over here is 2L divided by n. So you see, the number of loops equals the number of harmonics. That tells you the first one has one loop, the first harmonic. The second one has 2 loops. Okay, the number of loops equals the number of harmonics. So the fifth harmonic have 5 loops, the 10th harmonic has 6 loops, and so on. So from the number of loops, you can tell which harmonics it is, because the number of loops equals to the harmonics of a wave. Okay, all right. So it's not any wavelength that can give you this kind of wave. It's specific wavelength. This one, as you can see, is 2L. This one is 2L divided by 2. This is L. This one is 2L over 3. The next one will be 2L over 4, and so on. Okay, it's only this wavelengths that can give you a standing wave, not any kind of wavelengths. And that's because of the boundary condition we introduced it. We restricted the wave to be 0 over here. That's why the number of wavelengths that will give you this wave are restricted. Okay. Now, let's obtain the frequency now. Let's look at the frequency. How are frequency and wavelength related? The speed of a wave equals frequency times wavelength, right? Now, if you remember, the speed just depends on the property of the string, on the tension in the string, and on the mass per unit length of the string, right? So it's a constant for all the harmonics. The speed just depends on the tension in the string and the mass per unit length of the string, okay? So it's a constant for all of them. So we have lambda n, or let's say frequency, the n's frequency equals the speed of the wave divided by the n's wavelengths, okay? But lambda n, we just concluded, is 2L over n, right? So the frequency of the nth harmonic is this one, V divided by 2L over n, where n is harmonics, okay? So we get n times the speed V over 2L, okay? So this is the formula for the nth harmonic. The nth harmonic is n times the speed divided by 2L. Remember, V is speed of the wave, speed of the wave. If you're dealing with a string, you can use this formula calculated. If you're dealing with sound wave, then you know that formula, 331 square root of 1 plus T over 10 to the 3, okay? So if you know the temperature, you can calculate speed of sound. If you know the tension and the mass per length of the string, you can calculate the speed of the string, okay? Now, let's look at F1. F1 is 1 times V over 2L. This is it. This is F1. That is the frequency of the first harmonic. So you see the frequency of the nth harmonic is simply n times the first harmonic. So if you know the frequency of the first harmonic, you can reproduce the frequency of all the harmonics using this very simple recursion formula, okay? The frequency of the nth harmonic is simply n times the frequency of the first harmonic, okay? So the harmonics are basically the kinds of waves you get from a guitar, a piano, and so on. The reason music is pleasant to listen to is because the frequencies are integral multiples of each other, okay? That's why they sound good. All right, so this is the boundary condition where the wave is required to be 0 at the initiation point, or x equals 0, all right? Now, we're going to change our condition. Case 2. Case 2. We're going to say let x equals 0 be an antinode. Let x equals 0 be an antinode. Okay. Now we're looking for a wave like this. We have already concluded this is a node. Now we're looking for a wave like this, maximum over here. With like this, maximum over here. Okay. All right. So this is our condition now. Let the x equals 0 be an antinode. That is, we're saying let a net at x equals 0 would simply be a net, okay? The maximum value. Okay, that's what we're saying. All right, so let's work out this condition. First, let me give you an example like this. If you've got sound resonance in a pipe like this, okay, the wave cannot move over here. So you're gonna have an antinode over here. You've got sound wave over here. This over here is gonna be an antinode because the molecules are not allowed to move. But these molecules over here are free to move. So you're going to have an antinode at the end and a node at the closed end, okay? All right, so this is an example for this situation. If you've got a sound wave in a pipe, you're gonna have a node over here and antenna over here. So there's an application of this kind of a wave, okay? So now let's work it out. A naught is this one. 2a sine of, well, this absolute value, k L minus x. All right, and we're saying at x equals 0, this equals 0 over here should be 2a. Basically, this should be 1. We're saying the sign should be 1, okay? So this is our condition. Sine of k L, well, there's no L right now, equals 1. All right, when is sine 1? Sine is 0 over here, right? But this is absolute value. It can be -1 too, okay? So sine is 0 over here. It's 1 over here. It's -1 over here, okay? So you've got pi over 2, and then you've got 3 pi over 2. And then you keep adding 2 pi to this. So basically, these are the values. You got pi over 2, you got 3 pi over 2, you got 5 pi over 2, and so on. You see, it is half or integral multiples of pi. So generally, you can write like this one, 2n minus 1 divided by 2 times pi, okay? Where n is integer. Do you see that? If you put 1, you get pi over 2. 2 times 1, 2 minus 1, 1, you get pi over 2. If you get 2, you get 3. If you put 3, you get 5, and so on. So this is the general formula, okay? So this tells you this kn times L equals 2n minus 1 over 2 times pi, where n is integer, where n is integer, all right? But remember, the wave number is 2 pi divided by the wavelengths, right? So you've got 2 pi over lambda n times L equals 2n minus 1 over 2 times pi, okay? So pi goes away like this. And then let's cross multiply. It's 2n minus 1 equals 4, okay? Where is L? There's L somewhere. Oh, there's L over here. So this is for L over here, okay? So the n's wavelength is 4L over 2n minus 1. So you see, for this kind of wave, the n's, or the wavelength of the n's harmonic, is given by this formula, okay? For the first harmonic, n equals 1. This is the first harmonic. This is the first harmonic like this. You put 1 over here, you get lambda 1 equals 4L divided by 2 times 1, that's 1, right? So for the first harmonic, the wavelength is 4 times the length, okay? For n equals 2, the second one is like this. You'll have 1 loop. This is the second possibility. This is the second possibility, okay? And then you put 2 over here, you get 4L over 2 times 2, 4 minus 1, 3, okay? For n equals 3, the harmonic would be like this. You would have 2 of this, 2 of this like this, okay? And the wavelength would be lambda 3 for L or 5, and so on, okay? So for this kind of wave, this gives you the wavelengths that can give you this kind of wave with antenna on one end and node the other end, okay? Now let's look at the frequency. The frequency. Okay, the frequency, as you've seen before, is speed. Let's say for the nth harmonic will be divided by the wavelengths of the nth harmonic, right? So we'll just put lambda n in there. So the frequency of the nth harmonic is the speed divided by the wavelength, which is 4L divided by 2n minus 1, okay? That is 4L divided by 2n minus 1, all right? So that gives us 2n minus 1 and then you've got V over 4L. Okay, that is how you calculate the frequency of the nth harmonic. Now let's calculate F1. The frequency of the first harmonic is 2 times 1 minus 1 times P divided by 4L. But this equals 1. You see that? So this is simply speed divided by 4L. In other words, this one is F1. Okay? So you get this recursion formula. You've got Fn equals 2n minus 1 times F1. Okay? So for this kind of wave also, if you know the frequency of the first harmonic, you can generate the other frequencies using this formula very easily. For the second harmonic, will be, you put 2, you get 3. In other words, it's going to be an odd integral multiple of the first frequency, okay? So the frequencies of the other harmonics are an odd integral multiples of the first frequency, okay? So this is a situation where you have a node at one end and an antinode at the other end. And the example for that is a sound wave in a pipe open at one end and closed at the other, okay? So far we've been considering reflection from a denser medium, okay? We clapped it, so that's why we had reflection of denser medium. Now we're going to look at reflection from a less dense medium. Remember the difference, what's the difference, do you remember, of reflection from a denser medium and reflection from a lesser dense medium? What's the difference? Do you remember? No, from
Something to do
go
with
ahead, go ahead. Huh?
There is a phase change.
Very good. For denser medium, there's a phase shift of pi. For reflection from less dense medium, there is no phase change. Okay, there's a difference. If you've got a denser medium, it goes like this, it goes back like this. If it's less dense medium, it goes like this, returns the same way it came. Okay, that's the difference between reflection from a less dense medium and reflection from a denser medium. Okay, so we're going to look at reflection from a denser medium. Let me get this.
Excuse me, Professor, can you go back to the graph that you just painted?
This one?
Yeah. We can't,
okay,
because there is like a record thingy in the way, so.
Okay, can you see it now?
Yes.
Okay, let's say this, maybe let me put it like this. Let's say you've got a thin string over here and a thick string over here, okay? So you've got the reflection from a denser medium over here. So if it goes like this, when it goes back in the opposite direction, like this. There's a phase shift of pi. You see, it goes back in the opposite direction. But if it's the other way, let's say you have a thick string over here, and you've got a thin string over here. This is a reflection from a less dense medium. In that case, what happens is you got a wave coming like this. It doesn't go this way. It returns the same way. Okay, there is no phase shift. So it's being reflected from less dense medium, no phase shift. It's being reflected from a denser medium, like a clumpet, there will be a phase shift of pi. Okay? Do you see that?
Yes, sir, thank you.
All right. Okay, so now we're going to look at reflection from a less dense medium. Reflection from a less dense medium. The only difference is we don't have phase shift over here, okay? So let's say we're talking about the same problem over here. This is going to be L over here. Let's say they meet over here. So the incident wave will go this way, X, but the reflected wave will go all the way like this. So the distance traveled by the reflected wave will be 2L minus X, right? Or L plus L minus X. This is L, this is L minus X, okay, 2L minus X. So it's distance traveled by the reflected wave, this is distance traveled by the incident wave by the time they meet over here. All right, so the only difference with what we did before is that there is no pi right now, okay? So the incident wave would be Again, we're going to assume 100% reflection. Okay, A cosine omega t minus kx. This is distance traveled by the incident. And then the reflected wave would be A cosine of omega t minus k to L minus x. Now, the only difference is we're not going to add pi over here. Okay, this is reflection from a less dense medium. All right. Okay, so what's the phase angle for the incident is kx. The phase angle for the reflected wave is this one, k to L minus x, right? So the phase difference, the phase angle of the reflected wave minus the phase angle of the incident wave is k to L minus x minus kx, okay? So you've got 2kl minus kx minus kx, that is 2kl minus 2kx, and then we factor out 2k, you've got L minus x, okay? So this is our phase difference, okay? Now that we have the phase difference, we can obtain an expression for the amplitude, all right? And that amplitude, if you remember, that amplitude is the following. You've got A net equals, we're assuming both amplitudes are the same, so you've got A squared plus 2A squared, and then cosine of, now this is K times L minus X, right? Oh, there's 2 over here, 2KL minus X. All right, so this is our formula right now, okay? So we just want to simplify it, okay? We've got 2KL minus X. All right. Oh, there's also 2 over here. You've got A squared plus A squared, right? So you can factor out 2A squared, which will be root 2 times A. And then you've got square root of 1. Now you see this is plus now, plus cosine of 2KL minus X. Okay? And now we're going to use the double angle formula. Okay? We're going to use this formula. Cosine square X equals 1 plus cosine 2X divided by 2. Okay? Or if you decide to call y equals 2x, then this would be cosine squared of y over 2 plus 1 plus cosine of y divided by 2, or 2 times, okay? So we're going to replace this by this one, all right? So you've got A net equals root 2 times A, and then square root of 2 times cosine square of, there's a factor 2 over here, whenever by 2 will go away, you've got k L minus X. Okay, it's a function. And then, of course, I get 2a absolute value of cosine k L minus X. Okay, k L minus X over here. So this is the A net. You think this is the difference between this one and the other one? For the first one was sine. Now it is cosine. That's the difference. So if you've got reflection from a less dense medium, this would be cosine. And if you've got reflection from a denser medium, this would be sine, okay? Now let's look at the point of reflection. At the point of reflection, what do we have? Well, our point of reflection, x equals L, right? So A net at x equals L is what? You see, L minus L is 0. And cosine of 0 is 1. You see that? At x equals L, this is 0. And cosine of 0 is this one, 2a. In other words, we have a maximum amplitude at the point of reflection. So this tells you point of reflection is an antinode. Do you see that? At x equals L, this is 0. Cosine of 0 is 1. So at the point of reflection, we have the maximum amplitude. So the conclusion is the point of reflection, is an antinode. Okay, so for this kind of waves, you start the maximum over here. So it goes like this. It goes like this. You have maximum over here. We haven't put restriction over here so far. It could be anything over here, but over here it's going to be an antinode. Okay. And now we're going to introduce boundary values, boundary conditions. Okay. So let's look at boundary conditions now. Case 1, x equals 0 required to be a node. X equals 0 required to be a node. Required to be a node. Okay. So in this case, you're going to go something like this. You've got an antenna over here, but then you've got a node over here, like this. Okay. But we have already done that. We have already dealt with the case where one end is antinode, one end is a node. Okay, so it's the same thing. We're not going to do it again. Okay, we have dealt with this case. So you can use all the formulas. We use it for, you see, we had a node over here, and we required an antinode over here in the previous case, right? They're both the same. So you can use all the formulas for this case to this one. Okay, so you don't have to go through it again. It's all the same. Case 2. Case 2, x equals 0 required. X equals 0 required to be x equals 0 required to be antinode. Okay, antinode. So in this case, we have like this. So we already know this is an antinode over here. Okay, now we're requiring this to be an antinode. Okay, now we can go through all the process, but the formulas are exactly the same like the following. The formula for both ends nodes is the same like the case for the case where both ends are antinodes. Okay, so let me just give you an example for this one. An example for this one would be a sound wave in a pipe open at both ends. If you've got a sound wave open at both ends, then this will be antinode. The free vibrates over here. This is another the free vibrates over here. You'll get something like this. Okay, so you can use all the formulas we developed for this one, so we don't have to go through it again. All right, so we don't have to do anything with it because they're the same. All right, finally, we're going to look at a beat. Are you tired? Not yet? I got one more section. A beat. This is a wave with points of zero vibration separated by equal intervals of time. It's just like a drum. You see? Boom, zero, boom, zero, boom, zero. Okay? This is a wave with points of zero vibration separated by equal intervals of time. This is a wave with points of zero vibration separated by equal intervals of time, intervals of time. Okay, it's just like a drum. Okay, graphically, something like this. Let's say the wave initiates over here, then you get zero, another beat, you get zero, another beat, you get zero, and so on. That's what you call a beat. It is points of zero vibration separated by equal intervals of time. The only difference is for standing wave, you have X over here. But for a beat, you got time over here. Okay, that's the only difference. This would be like the beat of a drum. Okay, so when does this happen? This happens when waves of close frequencies interfere. Okay, a beat occurs when waves of closed frequencies interfere. Of closed frequencies interfere. Okay. So let's say we have two frequencies. What that means is their difference divided by one of them is much less than one. They're very close to each other. Okay. So let's say these two waves are the following. Let's say one of them is Y1. First, I think I've got something. Let me show you. I think I have something over here. Let me show you. Let's see if I have it over here. Standing wave speed. Okay. Okay, I've got a bit over here. You got this frequency 10T. This frequency is 10. You see that over here? And then this is 10.5, the second one. And then I added buzz in the third one. Okay, so we're going to use three functions over here. Okay, so you see the blue and the green are, the green has a frequency of 10. The orange has a frequency of 10.5. They're very close to each other. When you add them together, you get a beat. These are the beats. You see, 1 beat, 2 beats, 3 beats, and so on. So that's what we meant by this one. You get a beat when you add, let's say, two sound waves of close frequency. In this case, their difference is 0.5. So that's how you get a beat. All right. Let me see. All right, so let's say one of them is, again, we're gonna assume the same amplitude for both of them, just to make the discussion easier, okay? So you've got cosine, let's say this one is K1x minus omega 1t, and then let's say the other one is A cosine of Kx, K2x minus omega 2x, okay? Let's say these 2 points meet at the same point at the same time. So the result, Y net, is going to be the sum of these two waves, Y1 plus Y2, okay? So this would be, well, the sum of these two, okay? A cosine of K1 x minus omega 1t, and then plus A cosine of K2x minus omega 2t, okay? So what I want to do is I want to express it as a product of two cosine functions, because that way it's easy to interpret it. Okay, so, but how do we do that? I'm going to use the formulas for cosine of x plus y and cosine of x minus y. Okay, cosine of x plus y, if you remember, is cosine of x, cosine of y, minus sine x, sine of y, right?
Oh, Dr.
Okay.
Gebrselassie, can you move the pad slightly to your right?
I'm sorry. All right. So this is trigonometric formula, right? If you change it to minus, what do you get? X minus y. The only difference is it becomes plus. So you've got cosine of x, cosine of y, plus sine x, sine of y. Okay? Now let's add them together. So that gives me cosine of x plus y plus cosine of x minus y. You see, this goes away. This gives me 2 cosine of x times cosine of y. Okay? Now I'm going to say let x plus y equals a, x minus y equals b. Okay? So what I get? 2x equals a plus b, or x equals a plus b over 2. Okay? How about if I subtract them? I get 2y equals a minus b, and then I get y equals a minus b over 2. Okay? So that gives me so I'm trying to go from here to here. So cosine, so I've got cosine of A sorry. So this gives me cosine of A, cosine of B equals, then the x is A plus B over 2 and then A minus B over 2, okay? So you've got cosine of A plus B over 2, cosine of A minus B over 2, okay? So I'm going to use this formula to add these two functions. You see, I'm trying to add these two functions together, okay? So it's a product of sum, you see that? It's a product of sum and a difference of the frequencies, okay? So basically we get this one now. When you add these two, you get this one. So y net equals, so you get that cosine of, first you got the sums plus k2 over 2 times x, and then minus omega 1 plus omega 2 over 2 times t, times another cosine, which is a difference. You've got k1 minus k2 over 2 times x minus omega 1 omega 2 over 2 times t. You see, this is a product. Now, this omega 1 plus 2 is a very high frequency, but the difference is a very low frequency because we're saying the two frequencies are very close to each other, right? So this is a product of a high frequency function and a low frequency function, okay? So let's see what happens now. Let's say this is a high frequency function over here, the high frequency over here. Then you're multiplying it with a low frequency wave. Let's start from here. What do you get? You see, you're going to have zeros over here. Do you see that? So when you multiply this two, this low frequency wave with this high frequency wave, that's what we're going to get. You start from 0 over here, the amplitude starts increasing and then drops to 0. And then once again starts increasing, goes maximum and then drops to 0 because of the 0 over here, and so on. Okay, that's how you get a beat. It's a product of a high frequency wave, which is omega 1 plus 2, and the low frequency wave, which is omega 1 minus omega 2, okay? And we call this a beat. We call this a beat, okay? Now look, this is one period of the low frequency wave, okay? What do you think the relationship between the frequency of the beat and the frequency of the low frequency wave? This one is omega 1 minus omega 2 frequency. This one is omega 1 plus omega 2 frequency. So you see, this is one cycle from here to here for the low frequency, right? But there are two beats in one cycle. Do you see that? This is one cycle. This frequency omega 1 minus omega 2. But there are two beats in a cycle. What that tells you is the beat frequency is twice the low frequency. Okay? So our conclusion is beat frequency equals twice low frequency, or let's say omega 1 minus omega. This is frequency f1 minus minus f2. This is over 2, right? You see, this is frequency divided by 2. You see that? There's a 2, there's a factor of 2 over here. You multiply it, you just get f1 minus f2. So the beat frequency is the difference between the two frequencies. Do you see that? You see the frequency of the low frequency wave is the difference divided by 2. But there are 2 beats per cycle. You multiply it by 2, you get the difference. So the beat frequency is the difference between the frequencies. The beat frequency is number of beats per second, but in one cycle, you have 2 beats. So the frequency of the beat is twice the frequency, the low frequency wave, okay? So that's the main conclusion over here. Beat frequency equals to the difference between the frequencies, all right? Okay, I'm sorry for the interruption today, the phone, but that's it for today. Do you have any questions? No? All right, then I'll see you on Tuesday.
Thank you, sir.
You're welcome.
Have a good weekend.
You too. Bye-bye.
Bye-bye.